Good afternoon, everybody, and welcome to the session Side Channel Attacks on Symmetric Algorithms, Part 1. The first talk is going to be given by Jakov Belenki, and is titled Carry-Based Differential Power Analysis, CDPA, and its application to attacking HMAC SHA-2. Jakov, the floor is yours.
Thank you. Thank you for the introduction. I'm Jakov Belenki, and I'm going to talk about a very practical attack on HMAC SHA-2 in hardware implementation. This is an attack that we developed and tested as a research team of 45AQ. Let's start with some background. When we focus on ciphers like AES, rather than hash functions, it is widely recognized both in academia and in industry that the implementation by the book is vulnerable to side channel attacks, both in hardware and in software. Protection against these attacks is difficult, but in industry, it is clear to anyone who cares about security that AES must be protected against side channel attacks. Our subject today is hash functions, specifically the SHA-2 function, SHA-2 family, which is widely used. Hash functions do not necessarily need protection because they not always work with any secrets. But HMAC is a common way to use hash functions for message authentication. And part of the hash function input in HMAC is the secret key. So we have to worry about side channel attacks. Unlike AES, there are very few papers that show how to attack HMAC with side channel attacks. There are several reasons why it's hard to attack it. One reason is that the arithmetic addition, which is used in SHA-2, does not significantly amplify the difference between inputs, unless there is a big, large carrier propagation, which is rare. Unlike block ciphers, where change in one bit in the input to the S box completely changes its output. Another reason is that in SHA-2, two additions with the shared addend are performed in parallel. Some of the attacks try to bypass this problem, assume that the two additions are performed one after another, not in parallel, and then they can attack this sequential execution, which is good against software implementations, but naturally not against hardware implementations where the additions are performed in parallel. Other attacks do not assume sequential execution, but they assume chosen inputs. And in HMAC, it may be possible to choose the inputs to the inner hash, but not to the outer hash. For this reason, there is a kind of common belief that HMAC SHA-2 in hardware does not need protection. And we even know a case in which HMAC SHA-2 was certified without any checks. The first attack that we know of that can attack both inner and outer hashes in HMAC SHA-2 is our paper, which we presented in CHES 2021, and it needs a profiling stage. In this work, we present the attack, an attack on HMAC SHA-2 with several advantages compared to our previous work. We presented an attack on HMAC SHA-2 with several advantages compared to our previous work. The most important, no profiling stage is needed. The number of traces necessary to break HMAC is significantly lower than in the previous work. And in our experiments in software simulation, the attack was successful in 1,000 out of 1,000 cases. I'll describe the experiments later. As a central building block of our new attack on HMAC SHA-2, we designed a generic attack on arithmetic addition, which can be applied to other algorithms that include addition, for example, ARX ciphers. We call this attack CDPA, carry-based DPA. The full attack on HMAC SHA-2 described in our paper is based on CDPA, but is more complex. We extensively tested it both in FPGA implementation and in simulation. Because of the limited time frame of this presentation, I will describe only the basic CDPA attack. You can read about the full attack in our paper and even try it hands-on using our public repositories. The links are in the paper and in the end of this presentation. Let me explain the technical part. This slide shows a single round of the SHA-2 compression function. I won't go into the details of functions. It uses a hash function twice, once for the inner hash and once for the outer hash. CF stands for the compression function. What is important is that the first block in both inner hash and the outer hash depends only on the key, but not on the message. And the one who knows both internal states after the first block in the inner hash and in the outer hash, it is as good as knowing the secret. It makes it possible to forge any HMAC. We'll call these states the inner state and the outer state. We assume that the device performs one round per clock cycle, that we can provide uniformly distributed random inputs and can measure power consumption. For our attack, we are interested in the rounds immediately following the inner state and the outer state. These are the first points of time at which these secret states interact with the known input. This slide shows a single round function of SHA-2. I will not go into the details of functions F1 and F2. What is important is that the data dependent on the input word W is only on the red lines. The values delta A and delta E are constant and unknown. And the replacement of slot A with delta A plus W and slot E with delta E plus W is the only way how the input word affects the Hamming distance between the previous state and the next state. I'm not going to explain how to attack these two simultaneous additions. I will describe only a simpler attack on a single addition, and this is the CDPA. The CDPA problem is stated as follows. Let's suppose that a device contains two n-bit secrets, X and Y. And it performs a single n-bit addition of X with an n-bit input Y, W, and the result replaces Y. The side channel leakage is the Hamming distance between X plus W and Y. The goal is, given enough uniformly distributed inputs W, and corresponding side channel leakages, reconstruct X and Y. Note that the simultaneously flipping two most significant bits of X and Y does not change the Hamming distance. So these two bits cannot be found, only their XOR. So we are going to find this XOR of the most significant bits of X and Y, and all the rest of the bits of X and Y. The attack is based on the following observation. Let's denote the flipping the most significant bit by asterisk. It is clear that it changes the Hamming distance between X and plus W and W and Y by 1. Let's define dl of W as shown on the slide. It is a function of an n-bit argument that has exactly two changes exactly twice, and between these points, it is constant with values plus minus 1. In the places where this sign changes at the w axis, if we know where it happens, from these places we can derive all the bits of X, but the most significant one. And from the sign of dl at 0, we can derive the XOR of the most significant bits of X and Y, because there is no carry when we add with 0. Now, this observation is not the attack yet, because if we cannot choose the inputs, we cannot know even one value of function dl, let alone the precise points at which at the w-axis at which it changes its sign. Now, I'll describe the inductive step based of the attack based on this observation, which gives us a possibility to find the bits one by one. We number the bits from 0, starting from the least significant bit. And let's suppose that I minus 1 least significant bits of X are already known. And our goal is to find bit number I minus 1. And let's imagine for the moment that the addition between X and W is limited not to n, but to only I plus 1 least significant bits. If we knew the bit number I minus 1, which we don't know, we wouldn't know the pair of points at which the sign of dl changes. So there are two options for this pair of points, depending on the value of this bit. At the intervals between these four points, which are denoted here by mk, the function L dl is sure to be constant, and we can estimate its value as the difference between the values average values of L at sets mi and mi asterisk. In fact, the observed values of L of the Hamming distance cover not only the I plus 1 least significant bits, but the most significant bits as well. However, these most significant bits are random, and asymptotically they affect the average value of L at sets m and m asterisk in the same way. Their share is equal, and given enough traces, we will know the. First of all, we'll find the pair of points at which the sign changes, and we'll be able to tell +1 from -1. Putting it all together, we attack this in steps numbered from 1 to n-1 in this order. Before step I, we assume that I-1 least significant bits of X are known. And in particular, for step 1, we assume nothing. We divide the traces into 4 subsets based on the I-1 least significant bits of W. with the borders between the subsets where the carry bits into position I changes. We calculate the average observed values of DL at each subset, and from the pair of points at which the sign changes, derive bit of I minus 1x, ensuring the inductive assumption for the next step. Additionally, from the sign of DL at 0, we derive the XOR of bits I of x and y. And we need an additional step 0 in order to find the bit 0, because we have these XORs only starting from bit 1. Okay, I will not speak about the full attack, and I'll jump to the attack to our experimental results. We wrote a code in Python which collects simulated traces, optionally adds normally distributed noise, and then performs our attack on SHA-2 on simulated traces. We ran this code to test the success rate of the attack with different numbers of traces, different levels of noise, and different initial states. Later, after the paper was already submitted, we added a version of code which makes a full attack on HMAC SHA-2. In this version, if the attack is unsuccessful, we double the number of simulated traces until we succeed or reach a limit. You can find both versions of our code in the repositories. And it may help to, in order to attack, to understand the attack better, to run this code in the debugger. This graph shows how besides the attacks in the simulation, we performed attacks on an FPGA board, and here you see how the probability of success depends on the number of traces for both FPGA and simulated traces with different levels of noise. And we can see that the FPGA approximately corresponds to the noise level of 5 standard deviation. This graph shows four experiments that we performed. We made 4 experiments in simulation, each one with 1,000 traces, named HMAC SHA-256 with and without noise, and HMAC SHA-2 with and without noise. And you can see that the number of traces, each time we started from 2 to the 15th traces, and if unsuccessful, we doubled the number of traces until we reached 2 to the 30th. In fact, we never got more than 2 to the 28th. Even in the hardest experiment on 1 million traces, in 72% of cases, it was enough. The time was pretty low, even for the hardest experiment. The time in 97% of cases, the time was less than 2 to the 10th, that is 17 minutes. And it's like the rule of that 20% of people drink 80% of beer. In all 4 experiments, 15% of the traces took 85% of time, and 1% of traces took 50% of time. With such variation of the time, it makes much more sense to measure median time than the average time. So here you can see the median and the worst time for all 4 experiments, and you can see that even for the hardest experiment, in the half of cases, the attack took less than 33 seconds. Summing up. In order to attack HMAC SHA-2, we designed CDPA, carry-based DPA, applicable wherever arithmetical addition is involved. Based on CDPA, we designed and implemented an attack on HMAC SHA-2, both in simulation and on an FPGA board. And we had 1% success attacking HMAC SHA-2. Our conclusion is HMAC SHA-2 cannot be regarded as secure against side channel attacks unless properly protected. And any certification should include checking for vulnerability to the known attacks. If you are interested in our public repositories with the code implementing our attacks, or in 45Q's commercial products which test for the vulnerability to these and other attacks and which mitigate them, please visit the link shown in this slide. The mitigations against side channel attacks which we offer are based on the probably secure threshold implementation methodology. Thank you, and I will be glad to answer questions.
Thank you, Jakov, for the presentation. If you have any question, please feel free either to write in the Zoom chat or go to the microphone or raise your hand, and there will be people bringing the microphone to you. One question there.
Hi, you didn't precise what kind of adder you were using and if they influence the side channel leakage.
You mean how we implemented the adder in the FPGA?
Yeah, because even if in your model, I mean, there are several kinds of adders that you can implement for a 32-bit addition. And did you check the influence of that?
I cannot exactly answer your question now. I believe in our Verilog we just used the built-in addition. In any case, what we have is a proof of concept that at least for one implementation of addition in hardware, probably the default one, our attack works.
Thank you.
Are there other questions for Jakov? One question there.
Yeah, thank you for the presentation. My question is, how much your attack is depending of the leakage model? So the fact that the leakage can be written in the form Hamming distance between x plus y, x plus w, and y. So the Hamming distance between those two values. How much your attack is depending on that?
Okay, so the theoretical attack is based on the assumption that this is the leakage model plus maybe normal distributed noise. Now, of course, in the physical reality, the leakage model is not so. So the proof that the attack works does not necessarily apply to the physical world. But here we have experimental results that show that in the real leakage, we still are able to find the key.
Yeah, thank you. For your FPGA implementation, you developed the implementation so that you are satisfying this leakage model, or is it?
No, we just wrote implementation in Verilog, put it on FPGA, and FPGA worked as it worked, and whatever the leakage model was, that's what we measured.
We have time for one quick question. Yes, there in the first line.
Hi, my question is about the 2 rounds in 1 clock cycle case. Do you have any experimental results for that? Or
no, we did not perform experiments with FPGA. In the theoretical attack, there is a chapter on our paper where we describe how the attack should be modified to work with 2 round per clock cycle.
Okay, thank you.
Thanks. And let's thank Jakob again for the presentation. The next talk is RDS, FPGA routing delay sensor for effective remote power analysis attacks, and will be given by Ognon Jamochanin. Ognon, the floor is yours.
Okay, hello everyone. My name is Ognon, and today I'm going to present our paper RDS, FPGA routing delay sensors for effective power side channel attacks. This work was done in collaboration with David Spielman and our supervisor, Milena Stojlovic. So FPGAs offer many advantages. We have hardware level parallelism, we have reconfigurability that leads also to energy efficiency, and that's why they're being used to accelerate many different applications, from machine learning to genomics to big data, also image and video processing. And that's why also they're now available remotely in the cloud. So almost all major cloud service providers now have FPGA instances. And in these instances, currently we have single tenants. So the FPGA is shared between one single user and a shell, which would be kind of the host operating system. However, we've seen in the recent 10 years, many multi-tenant FPGA solutions that are being proposed to be able to maximize the resource utilization of these huge cloud FPGAs. And this is usually in a form of spatial multi-tenancy, where we have tenants that are co-located on the same FPGA, and they're, for security reasons, separated logically and physically. But that's not enough because the users are still coupled through the power delivery network, where voltage fluctuations spread across the entire chip. And this internal electrical level coupling causes security concerns in multi-tenant FPGAs. And it turns out that among other security issues, users can build and misuse low-level hardware from FPGAs to build voltage sensors, such as time-to-digital converters and ring oscillators, that essentially allow them to record now power traces remotely. So we no longer need to go with an oscilloscope for an FPGA, we can record traces remotely. And this opens the door to many remote now power analysis attacks. And we've seen in the last 7-8 years, many different attacks, such as statistical attacks, CPA, SPA, that try to extract secret keys. We have seen workload classification, where we want to, where previous work showed that we can identify which type of workload was done by a victim, and even attacks on machine learning acceleration. So where there were the architecture of neural networks was extracted, the input data folding, etc. So these sensors open up doors to many vulnerabilities, and that's why they're kind of the center of our talk. We try to see if we can make better sensors to sense voltage. So the typical sensors that are state-of-the-art right now use FPGA logic on hardware that are from these configurable logic blocks or CLBs in the FPGA. So it's either flip-flops, lookup tables, or carry elements. But FPGAs are also abundant in routing, and just as the logic is influenced by voltage, the routing is also influenced by this voltage. So we ask ourselves the question is, can we leverage routing to build a good voltage sensor? And this is this is our main contribution. We present the first routing-based voltage sensor called RDS, or routing delay sensor, which is free of placement and routing constraints, which makes it easier to deploy and port between different FPGA families, and more difficult to detect than current state-of-the-art sensors. And of course, it also outperforms TDCs in remote power side channel attacks. So this is the short outline of my talk. First, I'll introduce the state-of-the-art sensors, then introduce our architecture, show our experimental setup, and then discuss results and conclude the talk. So the current state-of-the-art voltage sensors are divided into two groups. One are frequency counters and the other are time-to-digital converters. Frequency counters are basically ring oscillators where we have an odd number of inverter in a loop. And because inverters are implemented using lookup tables in FPGAs, these are very slow, so they have low sampling frequency and low resolution. While time-to-digital converters, they consist of basically a tapped delay line. It's a chain of delay elements, and because it can be efficiently implemented in FPGA, they have high frequency and resolution, which makes them state-of-the-art for power side channel attacks. So let's look a bit into how these TDC sensors work. So assume we have a constant voltage on our FPGA, and we create a chain of buffers through which we propagate periodic signal or clock and sample that chain also periodically. Under constant voltage, the delay of these buffers here is constant, and the propagation of that clock throughout this delay line is constant. If the voltage, for example, lowers, the delay changes, and we have lower propagation. So the output in this case changes from 5 ones, which is equal 5, to, in this case, 3 ones, so lower propagation. On FPGA, usually only the end of the delay line is registered, which makes the sensor kind of have an observable delay line and an initial delay line, where the initial delay line is used just to delay the clock so that it enters the observable delay line. On FPGA, the initial delay line is implemented using lookup tables and latches because they're slow, so they allow low area overhead for a good shift in the clock. And the observable delay line is implemented using carry blocks to get fine resolution, which we'll discuss more. So what makes TDC's good voltage sensors? And we identified 3 main characteristics. One is a TDC has a monotonic increase of propagation delay. So from the input of the delay line, every next bit or every next element has a larger delay than the previous one. The next property is a wide observable window. So the delay between the last and the first element can be made arbitrarily large because we can just stack more and more of these delay elements. And the last part is high sensitivity, which is the most important part. So the delay difference between 2 consecutive bits or the delay of these delay elements is very low, can be made very low on FPGAs. And on FPGAs, carry logic allows us to make good TDC sensors. So here we have just an illustration of 2 connected carry blocks to explain why. Well, first of all, carry elements usually have a monotonically increasing delay in their outputs, which allows us to satisfy the monotonicity. Second is that they're abundant on FPGA, so we can put a lot of them and have a wide observable delay window. Then the carry elements have a very low delay between individual carry outputs. So in this case, we name it DIE, so which is the delay of the delay element. And another thing is that there exist direct routes between the carry output of one carry element and the carry input of the next one, which allows us to also satisfy this small DIE in case we hop from one carry block to the other. And finally, the routing from the carry outputs to the registers is also very short because they're dedicated paths from the carry output to the registers in the same slice. So overall, our sensitivity or DI, delta DI can be made very low using these carry chains on FPGAs. But the problem is to do so, first of all, we need to carefully place registers next to these carry 4 blocks. And second, we need to vertically place the carry elements because that's the only way we can use these direct wires between them. So these state-of-the-art TDCs can first only be vertically placed to obtain optimal sensitivity, have limited portability since we have constraints that are FPGA specific. So if we change FPGA families or vendors, we need to rewrite those, are easily detectable because we have a chain of carry elements and very carefully placed registers next to it, and have the sensitivity limited by the delay of the carry architecture. So we ask, is there a simpler or better way to do it? And RDS is our answer. So if I go back and say to the 3 points that we noticed that of what makes the sensor good is the monotonic delay increase, which a tap delay line by default satisfied however it's implemented. A wide observable time window is just increasing the number of delay line elements, and finally high sensitivity. To optimize high sensitivity, we need to decrease the delay between individual bits. So the question is, do we even need this tap delay line? Because the output, we just sum the bits at the output. So the order of those bits doesn't matter. If we have 110 or 101, it doesn't matter. So essentially, we don't need this monotonicity. And then the question is, can we then completely scrap these carry elements to build our sensor? And to optimize our sensitivity, or delta DI, if we look at this formula, if we simply remove the delay elements completely from the formula, provided that the routing is the DI-1 and DIR are similar, we can get really good sensitivity. And what it looks like when we take our sensor and transform it, it means that our tap delay line is simply replaced by routing. If we look at it in another way, this is our tap delay line where the DI, or the delay of the next element, is the delay of the previous element plus the delta DI. This can be also visually represented as the following. We have simply add a delta DI for each of the next registers. And what we do is when we use routing, this is just randomly shuffled. So we have this tree of routing that goes to individual registers, and it's very similar to what we want to achieve. And to do so, we essentially let FPGAs do the job, FPGA tools do the job in the spirit of having a portable and stealthy sensor. So we add simply this black box here, an area constraint, and say, place the sensor registers here, and let the FPGA placer do the job, and let the FPGA router route the wires. And we obtain a portable and stealthy sensor. So let's go quickly through the experimental setup. We use the multi-tenant threat model where we have the attacker and victim on the same FPGA. This physical and logical separation is enforced, but they're still connected through the shared power delivery network. As a victim, we choose a 128-bit AES. And as an attacker, the attacker uses either a TDC or RDS sensor. Both sensors that we use have 128 bits in their output registers. We use 3 different boards for our evaluation. One is Sakura X, which is the power side channel evaluation board. We use the Alva U200, which is a data center scale FPGA board. And finally, we use a small Basis 3 board, which we use it for temperature experiments, which we don't show in this presentation, but interested readers are encouraged to read it in the paper. So let's go into the results. Using the Sakura X board, we record power traces of AES encryption first. So here on the left, we can see the power trace of an RDS sensor, and on the right, we can see the power trace of a TDC sensor. So we are recording the same event, which is an AES encryption. And the AES encryption causes the same voltage drop. But we can see that for the RDS sensor, the output drops significantly more than the one of the TDC sensor. So the peak-to-peak ratio is much higher. And if we're recording the similar voltage drop, it means that we have better sensitivity because more bits flip to achieve this bigger voltage drop. And to evaluate how many more these bits change, we actually calculate the number of bits with non-zero variance at the output of each sensor. So here on the right of the figure, we can see from 0 to 128, these are individual bits of the sensor. And in red, it is the TDC. And we can see that there's only roughly around 11 bits that have non-zero variance across 100,000 AES encryptions. And these 11 bits are around this is where actually the clock edge lands in the observable delay line and moves left or right depending on the voltage. For the RDS, this number is 4x higher, more than 4x higher. And as we can see, the bits are scattered around the whole 128 bit output, the registers. So we have first of all, a bigger peak-to-peak, and also more toggling bits in the output of the sensor. More toggling bits means more bits carrying out information. So potentially RDS has more signal, picks up more signal than the TDC sensor. And to evaluate this, we calculate the signal to noise ratio on the last AES round, again using 100,000 traces in 5 different configurations. And we can see that even with the signal to noise ratio, RDS has around 2x higher signal to noise ratio. And this is particularly important in big FPGAs, cloud FPGAs, which by default have a very low signal to noise ratio. Finally, we also we run an attack, a correlation power analysis attack on the AES cryptographic core. We use a key rank estimation metric, which is upper and lower bounded. We run 5 different runs. So the top, the line here would be the worst upper bound, the line here would be the worst lower bound, and then we have the averaged upper and lower bounds. As many of you probably know, when the key rank converges to 0, we have successfully extracted the key. The more traces we need for it to converge, the worse the attack is, or the worse the sensor is. And if we compare RDS, which is here in red, which needs around 40,000 traces on average to break the key, TDC needs around 20,000. So on average, it outperforms, RDS outperforms TDC. To evaluate this on a more broader scale, we try varying also the placement first of the sensors. And here we can see in green the different 8 different sensor positions, and in blue is the AES position. And for these, in 80% of the rounds we ran, RDS is as good or better than the TDC. We also try to move the AES where the sensor is kept in place, but we also have 4 different AES placements. And in these also, in 87% of the runs, RDS is as good or better than the TDC. And so we can see that on average, RDS is better, but it also needs 30% fewer traces than the TDC to extract successfully the key. And as our final experiment that I'm going to present here is a correlation power analysis attack, but now on data center FPGA cards. The ones before were on the Sakura X board. We again use the key rank estimation metric, and we can see that, first of all, for the TDC, there's much less signal, and we, with 1.8 million traces, we break around 16 bits of the key. While for the, this is on average of over 25 different runs. And for RDS, this is 4x more, so we break slightly more than half of the key. So RDS outperforms TDC on these big data center FPGAs that have low signal to noise ratio. We also perform various other experiments in the paper, so if you're interested, feel free to read them. I encourage you. One of them was varying the number of RDS bits, because in the previous experiments it was 128. And we show that we try to attack with RDS 32, 64, 96, and 128. The more bits we have, the more successful the attack is, because there's simply more bits toggling and increasing the signal. We also evaluate the impact of temperature on our sensor. We evaluate the impact of different stable temperatures, but we also evaluate the impact of transient temperatures, so temperatures that are changing. And similar to TDC, RDS is not significantly impacted by the temperature changes. And for the same calibration, we've seen RDS operating successfully from -10 degrees Celsius to 80 degrees Celsius. And to conclude, RDS is the first stealthy routing-based voltage sensor. It is sensor-free of placement and routing constraints. So it means that it's easy to deploy and port between different FPGA families. It's more difficult to detect and eliminate because it doesn't have carry-based structures that we use. And finally, it has a better signal-to-noise ratio and better power side channel attack results than the state-of-the-art TDC. It impacts future work because it shows first that monotonicity is no longer required for voltage sensors in the sense of power side channel attacks. And finally, also it shows that detecting and preventing sensors is not sufficient to guarantee security, because current state-of-the-art detecting methods also include detecting carry chains, and we eliminated that. So it's kind of a cat and mouse game, so it's not enough to guarantee security. So thank you. Our sensor is openly available. There's also it's available also on the artifacts page of CHES, but also on our GitHub page. There is also a QR code if you want to access.
Thank you for the presentation. If there are any questions, raise your hand, write in the chat, and go to the microphone. There is one here in the second line.
Okay, thank you. Can you go to slide number 37, please?
Yep.
You passed it already, 37.
37. Okay,
Yes.
sorry.
Okay, thank you. 36. Yeah,
Yeah.
I completely understood the concept, but what I'm not getting is this is encoding, let's say, a variant of power consumption. In the TDC sensor, you have a very nice, let's say, transition from 1 to 0, and you know you can encode or decode this to something else and say this is a value that you have. But now here, there are some bits that they don't have any particular order because that the placer and router just decided to route them like that. And then how do you know that some actually bits are not very close to each other, and then there is some gap between the delay of the one line to another one, and you are missing something? And how do you actually convert this to real power values that you have shown that, okay, this is the power value compared to TDC?
Thank you. It's a very interesting question. The main part of the encoding of the output is just Hamming weight. So we sum the number of ones at the output. This means that the TDC, which has an order of ones then followed by zeros, and this, which has 1 0 1 0 1 1 1, however it goes, when we sum it, it's still the same value. And that's that's what we can see here. So there's an order, and here that it's just permuted, but we still sum it. Yeah.
There's a question there in the first line.
Thank you for the interesting talk. That was really amazing. My question is, I think I didn't get your point. If the leakage model is not Hamming weight, is it still possible to use the same sensor?
So this is not the leakage model. It's just the encoding of the output of the sensor.
I completely agree with you, but assume that I have one implementation with some leakage models.
Yeah.
Is it still possible to use this sensor for that? So it is model.
It doesn't. So the encoding of the sensor doesn't depend on any leakage model that we use. So particularly we use Hamming distance because we've seen that it works best with the AES that we have. So it really doesn't matter whether or not we haven't tried, for example, different attacks such as machine learning based attacks. But in theory, this is just a mechanism of recording power traces. So it should not impact. The leakage model should not be correlated with this.
Thank you.
There's a question over there, close to the end of in the middle.
Thank you for the great talk. And for the TTC, we know that there is a non-linearity and some bubbles in the chain. So for the routing, do you face the same problem? Does it affect the result? Thank you.
Yes, TDC has non-linearity, especially since carry chains are trying to implement the propagation as fast as possible. And the same goes with RDS. So we have not evaluated the linearity of our sensor, but because we let the tool decide which routes it's going to use, it is completely feasible that actually in this figure, there are some differences that are non-linear. What I have is one. What did I do? Okay. I have one backup slide which shows the distribution of the different delays, of the difference of the delays. Here it is. So on top we have the RDS, and on bottom we have the TDC. So we can see that both have non-linearity in them. This is the difference between in RDS when we order the bits and calculate the delta DIs, and on bottom is the TDC. So both suffer from non-linearity. But what we show in our results that it's not a big problem, at least for power side channel attacks.
Are there any questions? One question here in the first line. I know, yeah, well, you were there before, and then it's behind the column, so.
Hi, thanks for the talk. I have two questions. So did you try any sensors above 128 bits, or why did you stop there? And the second question is, I forgot. Go ahead.
Yeah. So we stopped at 128 because of our infrastructure. So Sakura X, we kind of hacked it a bit, but it uses 128-bit AES. So the word size that is communicated is 128-bit. On our to-do list is to definitely evaluate more bits. What we noticed is the difference between 96 and 128 bits is not as significant as between 32 and 128.
Thank you.
There's the last question here in the first line.
What about the frequency of the victim design? So are there any constraints on that?
So what we do is build a sensor. It's like we build a measurement equipment. We tested it on only one victim frequency, which is 20 megahertz. But my intuition is that it would not significantly change our results. Maybe it will change, of course, the number of traces needed to break the key, but the relative difference between RDS and TDC would not be significantly impacted.
Okay, let's thank Sognin again. The next talk is JIT-SCA, Jitter-based side channel analysis in picoscale resolution, and will be given by Dennis Gnad. Dennis, the floor is yours.
Introduction. I thought I had a screen here. Okay. So
Presentation, please.
am I supposed to press anything?
Just wait a second.
Okay, thank you for the introduction. So this work has actually been mostly, the implementation part has mostly done by my master student, Kai Schoß, who is not at the university anymore, and by PhD student Sergei Meshkov, who is sitting here at the front. Also together with Professor Tahori, and I am a postdoctoral researcher at KIT. I'm Dennis. So this is a work about jitter-based side channel analysis in picoscale resolution. So meaning we are using jitter of signals as side channel information. And what normally has been the case, that most of you know already, is that we have an oscilloscope, we measure our information through a direct physical access. However, this has been extended in recent years with attacks that work by using the shared power supply, even on-chip or off-chip. So what you have just seen by Ognen, it's an on-chip attack in which we implement sensors in FPGA fabric, and by that we can conduct power analysis. This has also been shown similarly off-chip. So if two chips are supplied from the same power supply inside one chip, you can also have similar sensors. However, similar things have been shown across more boundaries. For example, even through some wireless connection, there has been some leakage accidentally leaving the chip. And even through galvanic isolation on the other side, there were measurements shown that could attack the original chip. So, but usually all these attacks also measure analog properties. So even the attack we've seen at the last talk with the sensors, they indirectly measure some analog signal. So I come to also some details again. So for shared power distribution networks, we were exploiting FPGA fabric. For example, we can also use the noise of an ADC sensor in the same chip, or exploitation of power management is also well known by now. For shared power supplies, we have seen chips across the same PCB, but with the same power supply. They could be exploited through malicious firmware or through the other chip. Okay, and these works now, they work without physical access. You could just use firmware or FPGA configuration to do these attacks. And this goes even further. We have seen screaming channels. So I hope also most of you know the screaming channels attack, in which also we have a shared power domain inside the chip between analog and digital part, and the CPU, while it's computing some secret, it leaks some of these information into the analog power domain, into the radio, and this radio is then exfiltrating this power information to the outside, and by measuring that, you can do power side channel attacks remotely, which is, I would say, still a power side channel attack and not an EM attack, since the actual leakage happens inside the chip and then gets exported. Similarly, there were one attack was shown in which there is a galvanic isolation from a microcontroller chip. So with a microcontroller, it has a pin which has a fixed value, let's say fixed 5 volts. Then there's an optocoupler, and on the other side of the optocoupler, because it's still kind of an analog transmission, you have a lighting diode. On the other side, you measure this light, and then there's still some noise in it. This was shown to also be useful for a power side channel attack on the other side, despite there is no direct electrical connection. So in state of the art, what we've seen, I sum it up here again, we had the same chip power supply, we had something through galvanic isolation and wireless signal. However, most of these things have been using analog measurement, whereas we didn't see timing measurement. You could consider also in the last presentation you have seen, this is actually a timing measurement. So I put the X in brackets, so it's kind of a timing measurement as a surrogate for power. For galvanic isolation, however, we have not seen this. So this is the gap that we fill with this paper. And you might now ask why or when could this be relevant? And we think this is relevant when you consider digital transmission links. So you have a signal, and the signal goes through various layers or whatever. But on the other side, you can measure maybe just the time of the signal. For example, you have malicious firmware. You have something like a SerDes module, but you can still reconfigure it. There is some way that you have access to it, but you don't have a proper oscilloscope. And then you would be able to conduct an attack. So potential examples is HDMI. I write it here. Maybe it's not the most nearest example, but we used HDMI since we had the hardware for that. However, I can also think of optical connections. If they transmit the jitter information, they could also work. Same could be for Ethernet. But let's carry on and go to the details. So I just gave you an introduction. Next, I will go into more details of this attack, explain our experimental setup and the results of it, and then conclude this talk. So let's go into what is jitter. Jitter is actually an undesired factor in most digital communications. So if you send any signal and there's some edge, this is typically something that's coming from a clocked circuit. So at some point we see a clock, and this clock is the origin of this jitter, because depending on this clock, we set our signals, and depending on the signals, there will be an output signal leaving our circuit and go out into the world, let's say like this. And this has a small jitter because the clock has a jitter. Now we think this clock jitter is affected by power. And this exists actually in various transmission media. We see it in direct electrical channels. We see it in optical transmission. It can even exist in electromagnetic or acoustic signals. And it can be an extremely small quantity, so it can be very hard to measure. It can be something below 120 picoseconds. It's just some random number here, just that you get an idea of it. This was roughly what we saw in our experiments. Typically, it was even smaller. So if you have some measurement that is slower, you wouldn't even be able to see this kind of jitter. Okay, there's one work which has used a similar thing before. This was a work on CAN bus transmitter fingerprinting. Here, the authors of that paper, they were measuring a CAN bus and saw the jitter of the CAN bus transmitters, and by that they could identify which transmitter is sending the message depending on their jitter characteristics. By this, they essentially measured the manufacturing process variation in the sender. In this work, our goal here is to measure the data or power dependent jitter of the sender. So it goes not just into identifying a sender, but identifying what the sender of the signal is actually processing. For this, we use time to digital converters. So potentially it might work with other sensors too, but this is a good timing sensor. And in that, the signal propagates through a tap delay line, which is made out of carry chains. Typically, we have a clock, or we have any signal, and then a clock to sample this signal. So at some point, if we want to measure jitter, we also see a transmission from 1 to 0. And if this varies, like here, we see at some point there will be ones, there will be zeros again. And if this varies, we have a change at which position in this output we would see the clock edge. So the clock freezes the state of this output. We can then also measure voltage with that in the way that we just connect both together. So both the input as well as the sampling will be both the same clock. And this has been used for power analysis attacks, as we have seen before. However, in this work now, we want to be able to rule out this effect, since we want to prove that it's definitely the timing information that carries our side channel information and not any local power fluctuation or anything. So because for power sensor, you would see also the one propagating more to the right for higher voltage, to the left for lower voltage. Okay, now I've talked enough about this. Let's talk about TTCs for jitter measurement. If we want to measure now the jitter of a clock, which would be the simplest to measure, we need a PLL to filter the jitter. So PLLs are known to filter jitter. So if you have a clock input and put this clock to a PLL at the same frequency, there is some certain jitter rejection of this PLL, by which we can actually measure what the initial clock's jitter is, at least in relation to our PLL that we apply here. In this work, we then extend this as well to a complete separate tapped delay line, in which we use the same clock for both for input and for sampling, in which we would then not be able to measure the jitter of the incoming clock. Just as an experimental vehicle, keep this in mind for later. So yeah, keep this PLL in mind, and in the top, we can measure signal with a jitter. At the bottom, it's a signal without jitter. Okay, and then we can record traces. So if we make this every clock cycle, we get a measurement result of the jitter, which we can collect in a trace, like we are used to any side channel traces. Okay. We are looking at three adversarial models here. So the first one is the one you know from the previous work, actually. That's an attack that's happening inside a single chip. Here we have one part is an attacker module, the other part is a victim module. There is a communication signal. However, as the power domains are shared, we can probably not necessarily distinguish what is the leakage coming from. So what we need to do is we also need to separate the two devices and separate the power domain, so there would only be a communication signal. And if we want to be more serious, we would add a galvanic isolator to be sure that it's really the timing information and there's really completely separated power domains. However, that also means that we have an increase in isolation from left to the right. So let's come to our experimental setup and explain these three settings, these three setups in more details. The first one is this. You see, this is a single board. It's a Radeon ULX3S. That's some FPGA development board, a rather small board. And on the top, this, I hope this is the pointer. Yeah. So at the top, this PLL as jitter filter you've seen before. And then we have the two delay lines. One would be filtered and the other one wouldn't be filtered. Then we can collect two sets of traces and record them on our PC. On the bottom side, we have our victim, and the victim internally has an AES module that's getting a plain text and encrypting this plain text and also sending it to the PC so we can later run CPA. On the other hand, it also has this PLL that will export more or less the clock to the other half of the chip. So in the next setup, we now separate the power domains. We have two boards. At one side, we also use a HDMI signal. So the HDMI signal is NRZ encoded, so it's non-return to zero. It's a certain encoding scheme that most of you probably know too. So at the top, we need another board. So we use a Xilinx board, since this can receive on the HDMI port, since most FPGA boards, they had only output on HDMI, and it's pretty comfortable to use it, because in the next step, we add an isolator, and this isolator, you can buy it off the shelf. It's actually the most expensive of these three boards, the galvanic isolator, but you can get this HDMI isolator and you don't need to care about rolling something on your own. But here we have very separate power domains. We then even put two of these boards together, the bottom two boards in the EM isolation chamber, just to be sure that there's really no leakage. Okay, so let's go to the setup and the tech flow. What we do is we gather sensor traces while the AES module is encrypting. On the chip, we measure directly the connected clock, and off the chip, we use the HDMI link, where we measure a clock that's recovered from this NRZ signal. And each trace in the jitter is of the respective signal. Then in the end, we apply correlation power analysis. So this is the simple textbook attack from using CPA. However, we use also a bitwise model, which has also been common in this FPGA attacks, because it's known to work relatively good. Okay. So let's come to the results of this. Again, I want to show what was our hypothesis, what did we want to see, and do we actually see that? For the on-chip experiments, we assume that the unfiltered and the PLL filtered should show leakage, because the on-chip PLL that we use for filtering, it should still be affected because it's in the same chip. It should again be affected by power fluctuations. For the HDMI connected experiments, we assume that the unfiltered conditions should show leakage, but the PLL should actually filter the jitter out of the signal. And by that, it should also filter all the side channel leakage. So the jitter is assumed to contain side channel information and nothing else, because if something else would be there, something is probably wrong in our setup and we cannot prove our point. So why? Because only the victim transmitter power domain should leak. Okay, so for the on-chip attack, that's actually what we can see. So in the unfiltered condition, we can say that after about 27K traces, we can recover 1 byte of AES here, of the AES key here. In the PLL filtered condition, this actually increases a little bit, but this might be some measurement variation, because there's not too huge of a difference between 27 and 40K. So it's roughly similar. It's in the same ballpark. Then if you go through the HDMI connection, we actually see that we don't see anything when we filter it with a PLL. So at the bottom, we at least can't recover the AES byte below 1 million traces, but at the top, it's almost as good as an attack on the chip, which is pretty amazing. So in the end, maybe all the things we have done in this regard was mainly the jitter of our original clock signal. Now we continue this, and we have galvanically isolated HDMI. We put it even EM shielded, so there can also not be this kind of leakage. And here we see that with 47K traces, again, we can recover the AES byte. And it again, and it again fails below, at least below 1 million traces. And as it even goes to exactly the middle almost of this correlations, maybe this will never really show any leakage. Okay, good. Then let's come to a conclusion. In this work, we have mainly filled in this table. We have filled in this gap that we now use very fast timing measurements to be able to, from communication signals, get actually power leakage from the transmitter of that signal. So that was the main discovery here. And also galvanic isolation does not stop this jitter propagation, because if you have this isolator for HDMI, it's supposed to transport the initial signal in a as good as possible quality, so it wouldn't necessarily filter this jitter, right? PLLs, however, they can filter jitter, which only works for a clock signal, so this is not really a countermeasure for this problem. So there needs to be some other countermeasure. I think that quite simple things would be a countermeasure for this work. Like, we get the data, we save this data, we retransmit it, But if you have a direct connection, that shouldn't be really interrupted, like we have some signal switching or channel switching, then there is no easy way, I think, to prevent this leakage. Okay, so with this, I'm finished with the presentation. There's actually much more in the paper to read about, so I try to catch the essence of our paper. So if there are questions now or if you have questions later, feel free to ask.
Thank you, Dennis, for the presentation. Any question for Dennis? One, two.
You have this second delay line, which I understood you used as a control experiment.
Yes.
Could you also use it as a calibration reference in case there are common noise influences on both delay lines, that you compare the output of the two delay lines in order to improve your signal to noise ratio? That's sort of what I initially assumed you would be doing.
Oh, potentially that could be done. Yeah, I think it might be possible. Yeah. I think, yeah. Any more questions?
There was a question here in the second line in front.
Thank you, Dennis. My question is related to the delay, or let's say the amount of jitter that you have seen. Can you just, I mean, could you somehow measure how much or how large is the jitter? Because I'm a bit concerned if you give the clock from one board to another board, and then why do you give the clock? Because these two boards need to communicate with each other. If the jitter is very, very high, then they probably cannot communicate very well, because there might be some race, unless you do some other kind of ad hoc things or customized things to deal with the jitter from one clock, from one board to another board. Yeah, you may solve this, but if the jitter is very, very large, you may get this problem. But then how large was this jitter that you have measured, and you get the relation between this jitter and the amount of power consumption of the source board? In the range of picosecond, 10 picosecond, 100 picosecond.
Okay. So the question is first about how much jitter we had. So this is now a table that we also have in the paper where we record the amount of jitter. The red circle parts are what I have shown in the presentation. This is, however, now in bits of the sensors. We only know for one of the boards from some other experiments before how much one bit is in time. So it's mainly on the right side, I can say the measurement that was done on this Xilinx board, it should be about 11.5 picoseconds. And here you see the bits. So I'm sorry, I didn't make this calculation. So sorry. Essentially, I point to it. So in these cases here, you see the min and maximum jitter we have seen. So it's below, more or less below 1 bit. So it's the average minimum jitter. And here in this case, this is the mean plus standard deviation of jitter that we've seen. So if you see this here, it's about 5 bits. Yeah, for some reason, you see in the isolated case, we have more jitter than in the non-isolated. We don't really know where this is coming from. Okay. So maybe there's somehow this HDMI isolator actually even increases it somehow. But with 5-bit, it would be about 5 times 11.5 picoseconds. So it's about 50 to 60 picoseconds on average.
You didn't, for example, connect it to oscilloscope and then let it run and then sum them up all the clock and then see how much they really.
Actually, this is, if you think of it, our TDC is roughly sampling, let's say, at 80 gigahertz. Our oscilloscope is not that fast, so.
Okay, I see.
So I think with a 1 gigahertz oscilloscope, you see absolutely nothing.
Nothing. Okay.
Maybe we had a 4 gigahertz oscilloscope, so maybe the extreme cases of jitter we would see, but everything else would also be nothing. So this is actually a very small timing difference.
Okay, very good. Very good. Thank you.
Other questions for Dennis? There was a question there.
Thanks, Dennis. Great talk, great work. I was wondering two things. first one is in this isolated setup, have you thought about the possibility of simply the drivers, the buffers, the IOs that receive the signals, sharing information with the power and somehow having more coupling coming from other sources than simply jitter? Are you 100% sure that you're really managing to isolate jitter in these measurements?
We are relatively sure. That's why we did all of these experiments. Like we made these 3 boards, like I show it again. So if the IO, the input IO would receive more than jitter, this is, yeah, it's hard to say where it comes from, but it's actually time that we have. It's only timing because we separated all the power domains. We have a galvanic isolation board in the middle. It's powered. We put power banks to all of these things so that everything is really separated. They are not even plugged into their own wall power supply because we wanted to be extra sure. So then it means that the attacker on the IO input, it might be influenced from this galvanic isolator again, but in the end, it's still timing jitter, right? We could debate about this, but there's not a power connection.
Okay, okay. Thanks a lot.
We have time for one last question. There's a question there.
Just to confirm my understanding. Thanks for a great talk. Thank you a lot. We have you measure very small timing differences, but the limit on your setup is. I mean, does this still work if you're trying to measure a very high speed communication lane? Is this going to be harder if your target has a higher frequency? What at what point does this attack no longer work?
I'm not sure if I understood you correctly. It's acoustically a bit hard. You are asking if this works for higher speed signals, right?
Yes. What do I mean, I assume it breaks if something is sufficiently high speed, but do you need a high speed communication link or do you need a high speed victim, or does the attack just always work?
Here we have a not that high speed victim, but we have a high speed sensor. I mean, in this case, it's high speed. What we are working with is actually the natural delays of this delay line inside the FPGA. With the current setup, we are limited by this delay line. As you've seen in the last talk, there is possibility to improve that. And until, I don't know what are the limits, but then we can possibly also make faster time samples. And by that, we can also sample faster communication signals. Yeah.
Thanks.
Okay, this concludes the session. Let's thank Dennis and all the speakers of the session again. I'm sure that they will be available during the breaks for answering further questions. Thanks for joining.